It doesn't matter in which order you write it. I mean, you can put, in rows or in columns. If you transpose a matrix, that doesn't change the determinant. It's just, any sensible matrix that you can write will have the correct determinant. Okay, so what we need to know is the following thing. So we define something called the Jacobian of a change of variables. And use the letter J, or maybe a more useful notation is partial of uv over partial of xy. That's a very strange notation. I mean, that doesn't mean that we're actually taking the partial derivative of anything. Okay, it's just a notation to remind us that this has to do with a ratio between du dv and dx dy. And it's obtained using the partial derivatives of u and v with respect to x and y. So it's the determinant of a matrix u sub x, u sub y, v sub x, v sub y. The matrix that I had up there. Okay, and what we need to know is that du dv is equal to the absolute value of j dx dy. Or if you prefer to see it in the easier to remember version, it's absolute value of d of uv over partial xy dx dy. Okay, so this is just what you need to remember, and it says that the area in uv coordinates is worth, well, the ratio to the area in the xy coordinates is given by this Jacobian determinant. Except one small thing, it's given by actually the absolute value of this guy. Okay? So what's going on here? What's going on here is when we are saying the determinant of a transformation tells us how the area is multiplied, there's a small catch. Remember, determinants are equal to areas up to sign. Sometimes the determinant is negative because of reversing the orientation of things. But the area is still the same. Area is always positive. So the area elements are actually related by the absolute value of this guy. Okay, so if you find, minus 10 as your answer, then du dv is still 10 times dx dy. Okay, so yeah, I mean, I didn't put it all together because then you would have two sets of vertical bars. See, I mean, this is a vertical bar for absolute value. This is a vertical bar for determinant. They're not the same. That's the one thing to remember. Okay, any questions about this? No? Okay. So, actually, let's do a first example of that. Let's check what we had for polar coordinates. Last time I told you, well, if we have dx dy, we should switch it to r dr d theta. And we had some argument for that by looking at the area of a small piece of, a small circular sector. But, let's check again using this new method. So in polar coordinates, I'm setting x equals r cosine theta, y equals r sine theta. So the Jacobian for this change of variables. So let's say I'm trying to find the partial derivatives of x, y with respect to r theta. Well, okay, let me actually write them here again, just for you. And so what does that become? partial x over partial r is just cosine theta. Partial x over partial theta is negative r sine theta. Sorry, I guess I'm going to run out of space here, so let me do it underneath. So we said x sub r is cosine theta. X sub theta is negative r sine theta. Y sub r is sine. Y sub theta is r cosine. And now if we compute this determinant, we'll get r cosine square theta plus r sine square theta, and that simplifies to r. So dx dy is, well, absolute value of r, dr d theta. But remember that r is always positive, so it's r dr d theta. Okay? So that's another way to justify how we did double integrals in polar coordinates. Okay, any questions on that? Where? Yeah, okay.
Are we switching from polar to xy or from xy to polar? Flip from what it is from the top one.
Yeah, so this one seems to be switching. Well, it depends what you do. See, so, okay. Actually, here's an important thing that I didn't quite say. So I said, you know, we're going to switch from xy to uv. We can also switch from uv to xy. And, you know, this conversion ratio, the Jacobian, works both ways. Once you have found, you know, the ratio between du dv and dx dy, then it works one way or it works the other way. I mean, here, of course, we get the answer in terms of r. So this would let us, you know, switch from xy to r theta. But we could also switch from r theta to xy, just we'd write dr d theta equals 1 over r dx dy. And then we'd have, of course, to replace r by its formula in xy coordinates. Usually we don't do that. Usually we actually start with xy and switch to polar. But so in general, you know, when you have this formula relating du dv with dx dy, you can use it both ways, either to switch from du dv to dx dy or the other way around. And the thing that I'm not telling you, but now I should probably tell you, is, you know, I could define two Jacobians, because if I solve for xy in terms of uv instead of uv in terms of xy, then I can compute two different Jacobians. I can compute partial uv over partial xy, or I can compute partial xy over partial uv, if I have the formulas both ways. Well, the good news is these guys are the inverse of each other. So, you know, the two formulas that you might get are consistent.